Hello everyone. In this video we will continue with the estimate sequences framework that we started looking for proving the accelerated gradient descent. We will specify the exact form of phi t function for which we constructed an iterative update rule in the last video. To recap, we said that a sequence phi t, lambda t, xt is an estimate sequence if it satisfies the following upper and lower bound conditions, which is that f of xt is less than equal to phi t of x, which is less than equal to 1 minus lambda t into f of x plus lambda t into phi 1 of x. The property is such that it directly implies that the optimality gap decreases as order of lambda t. To find an estimate sequence, we need to ensure both the upper and lower bounds. Of these, the following template for generating the approximating functions phi of t. Phi t plus 1 of x is equal to 1 minus beta t into phi t of x plus beta t into L of x comma yt, where beta t is greater than 0 and L of x comma y is the lower bound on f of x, so that f of x is greater than equal to L of x comma y for all y, along with the definition of lambda t, which is that it is the product from I from 1 to t minus 1 of 1 minus beta I, and lambda 1 equal to 1 ensures the upper bound property. So we have already seen the proof of this statement. Recall that the lower bound L can be f of y plus gradient f of y, comma, x minus y for convex functions, and it can be replaced with the quadratic lower bound for strongly convex functions. Next, we see that it is possible to have quadratic phi t functions that can approximate f as required. So far, we have established that to satisfy the upper bound condition, the phi t sequence has to be constructed as phi t plus 1 of x equal to 1 minus beta t, phi t of x plus beta t into L of x comma yt. Now look at this expression carefully and observe that for convex functions, L is either linear or quadratic. Therefore, if we choose phi 1 as quadratic, then this definition ensures that all successive phi t will also be quadratic. So let us choose phi 1 of x as equal to phi 1 star, which is a constant, plus gamma 1 by 2 norm square of x minus x1. So here phi 1 star and gamma 1 are some parameters that will be specified later. The form of phi 1 allows us to postulate that phi t will be of the form phi t of x equal to phi t of star plus gamma t by 2 norm square of x minus zt for some zt such that z1 is equal to x1. So let us see if this is possible. The advantage of this form is that we will immediately get that phi t star is equal to min of phi t of x, and this minimum is actually attained at zt. So zt is equal to arg min of phi t of x. But if in the process of verifying this form we get to a contradiction, it would imply that this simple form would not be possible. So let us expand the left and right hand side equations to get phi t plus 1 star plus gamma t plus 1 by 2 norm square of x minus zt plus 1 equal to 1 minus beta t into phi t star plus gamma t by 2 x minus zt norm square plus beta t into f of yt plus inner product of gradient f of yt comma x minus yt. Now to ensure this equation is true, we need to find the various parameters. Observe that the two sides are quadratic functions of x, so we can match the coefficients of the quadratic linear and constant terms with respect to x on both sides, and that should tell us the various parameters and their choices. So first we match the quadratic expression, so the quadratic coefficient that is multiplying norm of x square, so as to obtain gamma t plus 1 is equal to 1 minus beta t into gamma t. Then we match the linear term, that is the term that depends on x, so as to obtain zt plus 1 equal to zt minus beta t by gamma t plus 1 into gradient f of yt. Finally, whatever remains are the constant terms, and we can match them so as to obtain that phi t plus 1 star is equal to 1 minus beta t phi t star plus beta t into f of yt minus beta t square by 2 gamma t plus 1 norm square of gradient f of yt plus beta t times inner product of gradient f of yt comma zt minus yt. So as we can see here, it is always possible to choose the parameters in this way, implying that the form of phi t, the quadratic form that we postulated, works out and is possible. So at this point we have the exact form of phi t which satisfies the upper bound inequality and is consistent for all t. So it remains to establish that the phi t specified earlier satisfies the lower bound condition also. That is that f of xt is less than equal to phi t star, which would imply that f of xt would be less than equal to phi t of x for all x. So for proving this statement, we will again proceed inductively. First, to ensure that it is true for t equal to 1, we can choose phi 1 star is equal to f of x1 so that it will be true for t equal to 1. Now suppose that it holds for some t and we need to establish it for t plus 1. So in other words, we need to bound f of xt plus 1 minus phi t plus 1 star in terms of something that depends on f of xt minus phi t star. Let us consider what we need in order to go from t plus 1 to t. Note that we have not yet decided how to choose xt plus 1, and also we have not decided how to choose yt. But we know so far that the gradient is being evaluated at yt. So we need to bound f of xt plus 1 in terms of f of yt, and we would need to bound that in terms of f of xt. So for the first bound, we need to decide how to express xt plus 1 in terms of yt. Taking cue from the gradient descent method, a valid choice seems to be that xt plus 1 equal to yt minus 1 over L gradient of f of yt, for which case it would hold that f of xt plus 1 is less than equal to f of yt minus 1 over 2L norm square of gradient f of yt, which is the result that follows from the quadratic upper bound and smoothness of f. Then the second bound, which is between xt and yt, can be obtained by using convexity. So we can use the fact that f of yt is less than equal to f of xt plus inner product of gradient f of yt comma yt minus xt. So now we can put all of these together. First, let us use the definition of phi t plus 1 star to get that f of xt plus 1 minus phi t plus 1 star is equal to f of xt plus 1 minus 1 minus beta t phi t star minus beta t f of yt plus beta t square by 2 gamma t plus 1 norm square of gradient f of yt minus beta t into inner product of gradient of f of yt comma zt minus yt. Now we can use the xt plus 1 update and the smoothness condition to bound this as the right hand side is less than equal to f of yt minus 1 over 2L norm square of gradient f of yt minus 1 minus beta t into phi t star minus beta t into f of yt plus beta t square by 2 gamma t plus 1 norm square of gradient f of yt minus beta t times inner product of gradient f of yt comma zt minus yt, which can be written as equal to 1 minus beta t into f of yt minus phi t star plus beta t square by 2 gamma t plus 1 minus 1 over 2L into norm square of gradient f of yt minus beta t into inner product of gradient f of yt comma zt minus yt. And finally we use the convexity of f and the induction hypothesis to get that this quantity, this right hand side, is less than equal to beta t square divided by 2 gamma t plus 1 minus 1 over 2L into norm square of gradient f of yt plus inner product of gradient f of yt comma 1 minus beta t yt minus xt plus beta t into yt minus zt. So just by looking at this form, it is clear what needs to be done. We need to make the coefficient of the first term non-positive and the second term to be 0. So setting the second term to 0, we get that the yt is convex combination of xt and zt, that is yt equal to 1 minus beta t into xt plus beta t into zt, which is what we had earlier. Also, for the first term to be non-negative, we required that L beta t square is less than equal to gamma t plus 1. So that is all the conditions we needed. It remains to ensure that this choice of parameters is not self-contradictory. First, we consider an example set of parameters that gives us the desired rate. Let us consider beta t equal to 2 over t plus 3 and gamma 1 equal to L. Then it can be seen that lambda t plus 1 is equal to product from I equal to 1 to t of 1 minus beta I, which is equal to 2 by 4 into 3 by 5 and so on till t plus 1 by t plus 3, which evaluates to 6 divided by t plus 2 into t plus 3, which is basically an order 1 over t square quantity. And for this case, you can verify that beta t square is less than equal to lambda t plus 1. So in this example, we have seen that we can also get the required rate of order 1 over t square with this choice of parameters. Another possibility is that we choose beta so that this is an equality for all t, that is L beta t square is equal to gamma t plus 1. It can be verified numerically that such a choice is also possible and gives us the same order 1 over t square convergence rate. So before concluding, let us summarize the estimate sequence approach. For the unconstrained problem, the following process was followed. First, we specified a recursive update rule, that is phi t plus 1 of x equal to 1 minus beta t into phi t of x plus beta t into L of x comma yt, and showed that if we choose lambda t plus 1 is equal to 1 minus beta t into lambda t, then this rule satisfies the upper bound requirement. Then we said that we will consider quadratic phi t functions of the form phi t of x equal to phi t star plus gamma t by 2 into norm of xt minus zt square, which if we combine with the first condition, we will get the way in which phi t star, gamma t and zt must be selected. Finally, we selected beta t by ensuring the lower bound condition that f of xt is less than equal to phi t star for all t. So these are the three broad steps that we need to follow whenever we are developing any algorithm from scratch. Note of course that the resulting algorithm will depend on the choice of phi t in steps 1 and 2. In fact, you can verify that if instead of yt we had used xt in the lower bound, then we would have obtained the classical gradient descent instead of the accelerated version. So far we have seen two styles of proofs. Let us compare them. Let us see how proofs that adjust parameters using telescopic sums compare with proofs that are based on estimate sequences. Clearly, the telescopic sum based proof is shorter, while that using estimate sequences is longer and involves more number of steps. So when should we use which kind of proof? The telescopic sum style proof is useful when the form of the algorithm is known, but you need to figure out the optimal parameters. Naturally, it does not help us understand the update equations, but it is a short proof and there are less avenues for making mistakes. The estimate sequence proof is constructive, so is useful when the form of the update equation is not known at all. So if the update equation of the algorithm is completely unknown, then it is better to use proof that is based on estimate sequence and construct the algorithm along the way. The proof based on the estimate sequences provides a mathematical reason behind why the updates should be carried out and how they should be carried out, while the telescopic sum based proof is simpler but does not provide any such intuition. A possible approach is to first find the optimal form of an algorithm for the simplest unconstrained case and then switch to the telescopic sum style proof for all the different variants, such as projected, proximal, or mirror versions. So that is all for this video. We are done with looking at various proofs for the accelerated gradient method. In the next video, we will look at the idea of smoothing and how it helps in speeding up the convergence for non-smooth problems.